So hello, today we're going to start up the last class. The last time you have to sit here and listen to me drone on in my boring ways. Um, so that's cool. Um, Reminder, there is a review session Friday at 3, so it's not the last time you can listen to me drone on, since I'll do that then too. I plan on going through last semester's final. As I go through last semester's final, give some hints. I'm gonna try to keep it at an hour. I might go a little over. Like when I did the reviews as for physics, I went an hour 5 minutes. But I'll try to do pretty close to an hour. I will be recording it, so if you can't make it or just don't want to make it, that's fine. You don't have to. It will be on YouTube. And then your final exam is Monday, the 10th at 12:30. Any questions about that stuff before I get into it? Got noises but no questions? We good? Okay. Let's get into it. What we were talking about was different types of chemical reactions. And we talked about combination, where two things should come together, and decomposition, where one thing comes apart. And we're going to continue with probably the most fun chemical reactions, combustion. When you talk about explosions, what an explosion is it's anytime there is an exothermic reaction, liberating extra energy and doing all of it basically all at once. A combustion reaction is anytime something combines with oxygen and bursts in flames, and will always be a compound with oxygen. Earlier we talked about the burning of natural gas. That was a combustion reaction. That natural gas plus oxygen gives the CO2 and H2O. What happens is it does have a catalyst of heat. That's what the little triangle means over the arrow, that you need a spark to start it. But once you do, it produces a ton of heat. A ton of heat, which is fire. That's what happens when you burn natural gas. A kind of fun one, and you know what? Let's put on the audio for this. Um, a kind of fun one. This is one I did myself a little while ago. Is sugar has a combustion reaction with oxygen. It only happens in very heavily oxygen rich environments. You need to have a ton of oxygen. You can do that by just heating up potassium carbonate, which I did here. And what I'm holding in those tongs is a gummy bear. And this is me just dropping a gummy bear in a very oxygen rich environment. There's other chemicals in there, but it's only the oxygen matters. It's something that's basically pure oxygen.
It did nothing to you.
I mean, yeah, sugar does a combustion reaction. You put sugar in a heavy oxygen-rich environment, you get sparks. Um, there's the reaction. You do need 12 oxygen molecules for each sugar molecule, which is why sugar just doesn't explode in the air. It needs to be very oxygen-rich. Now, in general, combustion can do a whole bunch of stuff. What we're mostly going to talk about is the combustion of hydrocarbons. A hydrocarbon is any compound that is just hydrogen and carbon, hence the name. And hydrocarbons are one you can predict. The combustion reaction for any hydrocarbon will always be the hydrocarbon will mix with oxygen gas and will produce carbon dioxide gas and water vapor. Anytime you take anything that's C and an H with any ratio of C to H, if you want to find its combustion reaction, you just say plus O2 gas yield CO2 gas plus H2O gas. The only trick after that is balancing it. Methane, natural gas, there's the reaction. Gasoline, burning gasoline, there's the reaction. Anytime I give you C something, H something else, if I ask you to predict the reaction, it will be plus O2 yields CO2 plus H2O. And I'm going to have that on the homework and possibly on the exam. what is this combustion reaction? And just say plus O2 yields CO2 plus H2O. The only trick, as I said, is balancing it. I recommend start with balancing the carbons, then balance the hydrogens, then balance the oxygens. And you should usually work out. Any questions? Okay, I said I was going to do 5 types of reactions with 3 in. Let's go to the next one. The next one is called a double replacement. You see, a double replacement reaction is a reaction where you have 2 ionic compounds and their cations swap. See, we can say an ionic compound is a mixture of a cation and an anion, the positive ion and the negative ion. What a double replacement is, just as I said, the cation swap. That if I had A linked with B and C linked with D, I now have C with B and A with D. Normally, these are 2 ionic compounds, and when they are, you will always end up getting a solid piece forming, calling a precipitate. Oops. Well, that works. Take, for example, this reaction. If I have silver nitrate and sodium carbonate, what's going to happen when silver nitrate and sodium carbonate mix is this silver is going to go to the carbonate. This sodium is going to go to the nitrate, giving you silver carbonate and sodium nitrate. And when this reaction occurs, you'll have 2 things. They'll always start aqueous, but your product will be, one will be aqueous and one will be a solid. Once again, the solid called the precipitate. This weird gooey gray stuff, that's the precipitate in this reaction. Now, just because you put 2 ionic compounds together doesn't necessarily mean they're going to react. It'll only react if a solid is formed. How to figure out if a solid is formed, aka will they react, is all based off what is called the solubility rules. The solubility rules is just a list of things that are dissolvable in water. This means any compound that starts with lithium, sodium, potassium, rubidium, or ammonium, or any compound that ends in nitrate or acetate. Anything that follows those rules will dissolve in water. If it does not follow through one of those rules, well, there's a few other things if you get more complicated, but I'm not going to get into with weird exceptions. But everything else for your case will not dissolve in water, and that means that will be the precipitate. And if I give you a double replacement reaction, it's actually not, it's a little annoying, but not too complicated to predict the product. And so that's something else I may ask you to do. Take, for example, this reaction. Barium chloride and potassium chromate. If I mix barium chloride and potassium chromate, I can say exactly how this reaction should happen. The process will be as follows. Start by collecting your ions, your cations and anions. See, what I'll say here is, and let me pull up my periodic table, is the first thing is barium chloride. Barium chloride is a mixture, and let me put on this, and we'll go green, I think shows well with this. Barium chloride is a mixture of barium and chlorine. Barium is in family 2A, so when it ionizes has a charge +2. Chlorine is a nonmetal in 7A, so when it ionizes has a charge -1. I also have potassium chromate. Potassium is in family 1A. It has a charge +1. Chromate, well, I'd have to look it up for my polyatomic ions, but chromate, once again, if I look it up for my polyatomic ions, chromate has a charge -2. And so that means if I have barium chloride plus potassium chromate, I'm starting with a barium with a charge +2, a potassium with a charge +1, a chlorine with a charge -1, a chromate with a charge -2. And what I'll do is I'll swap the cations. I'll say originally barium was with chlorine. So now barium will be with chromate. Initially potassium was with chromate. So now potassium will be with chlorine. Is this making sense so far? Any questions? Now, keep in mind when I put them together, I got to watch the charges. If I have barium with chromate, that's a Ba +2 with a ClO4 -2. Which if I do the cross method, they should both be a 2. But keep in mind when you can reduce. And if I have K and Cl, that leads to KCl. Now note, I don't just say K2Cl2. I don't just blindly match them. I have to go and watch the charges. But those will be the compounds I get. I'll get barium chromate and potassium chloride. I can also add the phases. See, if I take my solubility rule, I know anything with potassium in it dissolves in water. That means KCl can dissolve in water. That means KCl must be an aqueous solution. And if that's aqueous, the other one is a solid. Always on this, use this table, have this table with you. And whatever is on that table, that will be a Q in a double replacement. Whatever is not on that table, that will be the solid. And there we go. That's the reaction. Now, this answer isn't 100% correct. What's wrong with this? Anyone know what's wrong with this answer? Anyone? This is the fun interactive class I so love. So, what's wrong with this is that take a look at what I have on each side. I have 2 chlorines here. I have 1 chlorine there. This isn't balanced. Always make sure you balance your equation. I have 2 chlorines. I also have 2 potassiums. And so to balance it, I'm just going to shove a 2 right there. This is now a balanced equation. So on the homework and possibly on the exam, I might give you the reactants of a double replacement reaction and ask for the products. If I do, write down your ions, your cations, your anions, swap the cations, put them together, and balance, and make sure you check your phases. Any questions though? Okay. So this, as I said, is a double replacement reaction. If I don't just say replacement reaction, but say double replacement reaction, there's probably other types of replacement reactions. And our 5th and final type of reaction will be the single replacement reaction. You see, where a double replacement reaction was 2 ionic compounds, a single replacement reaction is 1 ionic compound and a lone metal. What's going to happen in a single replacement reaction is the lone metal and the ionic compound will swap places. Oh, sorry, the cation will swap places. That the lone metal and the cation will swap. There's one kind of exception to that, which is a little more complicated. I'll come back to in a second. Now, this doesn't always happen. Whether or not it happens is based off something called the activity series. The activity series is a way to measure how reactive something is. And what it says is how greedy things are to be in compounds. It's just a listing of metals plus hydrogen. I'm going to come back to that hydrogen in a second. But it's just a listing of metals that says how much do they want to react. The higher something is in the activity series, the more it wants to react. And what that means, the higher something is in the activity series, the more it wants to be in a compound. Here is the activity series. Lithium is the highest. The general idea is you're in a single replacement, going to have a lone metal and an ionic compound. And either nothing is going to happen, the lone metal will stay the lone metal, the ionic compound will stay the ionic compound, or they're going to swap. The lone metal will say, screw this noise, I'm getting in that compound, kick the cation to the curb, and make it go be on its own. In a single replacement reaction, whichever cation is higher on the activity series, whichever one is higher on the activity series will end up in the compound. If it's already in the compound, nothing happens. If it's not in the compound, it'll goddamn fix that and get in that compound. Now, hydrogen is on here. Hydrogen is a nonmetal. But hydrogen, because of the way it bonds, you can pretend it's a cation. You can pretend hydrogen's a cation with a charge +1, even though it's not. If you do so, hydrogen will work. This actually is why most acids respond to metals. It has to do with the activity series. In fact, you can treat water. I'm going to get ahead of myself, but this is kind of a neat thing. You can treat water as instead of H2O as HOH. If you treat it as HOH, which is mixing an H +1 and an OH -1. If you mix potassium with water, as in K solid plus H2O liquid, what happens is if we pretend water is this HOH idea, you can see that potassium is higher than hydrogen. What that means is if you mix potassium with water, this happens.
Is if I try to take a piece of pure potassium metal, which I have here, pretty decent sized piece, this might be big. I'm going to move this a little further away. And just mix it with water. A single replacement reaction will occur. The potassium will pull the hydrogen out from the water and replace it. And what will instantly happen is that reaction, because it's so exothermic, will just heat up. And the hydrogen gas, that wasn't that impressive actually, but the hydrogen gas will catch fire.
And that's the idea. It burns the hydrogen gas. It's just a single replacement reaction. Now, in general, whether or not these reactions occur, all based off the activity series. Take, for example, if I mix iron and copper sulfate. If I mix iron and copper sulfate, I can say iron is right here on the activity series. In copper sulfate has copper. Copper is right here in the activity series. That means iron is higher. Iron wants to be in the compound. And if iron is not in the compound, it'll say, screw that noise, I'm getting in that goddamn compound. And a single replacement reaction will occur. This is what that looks like. This is iron mixed with copper sulfate. It looks like we're growing copper because we kind of are. Now, the products will always be an aqueous and a solid. You'll start with an aqueous and solid, you'll end with an aqueous and solid. The only exception is if it's hydrogen, hydrogen will be a gas and not a solid. Questions on this so far? If I instead put together just iron sulfate and copper, nothing's going to happen. Iron is high on the activity series. It's going to make sure it ends up in the activity series, in the compound. If it's already in the compound, it's going to say, cool, we're good, don't need to do shit, and we'll just stay as is. One thing to watch here, though, is you do need to watch your charges. Let's say you mix aluminum and nickel sulfate. If I mix nickel and aluminum sulfate, I am mixing, sorry, aluminum is nickel sulfate. Aluminum and nickel. As you can see, aluminum is higher on the table. So aluminum will end up in the compound. But I still need to watch my charges. When you do this, always check your ionic charges. See, aluminum has a charge +3. Nickel has a charge -2. And sulfate, I can look up, has a charge -2. Sorry, nickel is +2. I misspoke. Nickel is +2. Sulfate is -2. When they swap, the aluminum and the nickel will swap, but I still need to watch my charges. I'm still going to have to say, if I mix together aluminum and sulfate, it's Al2SO4 3. That I still need to make sure my ionic compound is possible, that the charges still make sense. and I still need to balance. Questions? I'm used to a lot more questions on these. But if you have no questions, that's pretty good, because that means you probably must understand it if you don't have any questions. So, that's cool. Now, as I said, this normally is with a metal and ionic compound. The exception is things that begin with hydrogen. That metals and aqueous acids can also do this. When they do, you end up with hydrogen breaking free. Basically, you just pretend hydrogen has a charge +1. That's an ionic compound. It's not, but you just pretend. And it actually works pretty well. Of note, hydrogen will be a gas, not a solid. This is why, like in the movies and stuff, acids always eat through metals. Acids eat through metals because the acids want to do the single replacement reaction. And in fact, any metal will react with an acid if the metal is higher on the table than hydrogen. Acids will not eat through copper, silver, platinum, or gold because hydrogen is higher on the activity series. But it will eat through lead, tin, nickel, iron, chromium, zinc, aluminum, magnesium, sodium, calcium, potassium, or lithium. Okay? So there you go. 5 types of reactions. All but one of them, I expect that if I give you the reactants, you can give me the products. Those being combination, which you can predict, decomposition, the only one you can't predict, combustion of hydrocarbons, single replacement, and double replacement. So a combination, you take 2 things, shove them together. Decomposition, you take one thing, you break it apart. Combustion of hydrocarbon, you just add to a hydrocarbon O2 to yield CO2 and H2O. Double replacement, you swap the cations. Single replacement, you swap a cation and a loose metal. Any questions on all this? Okay, so we're halfway through today's class, and I have wrapped up all these reactions. So it shouldn't be too surprising that I have something else planned. For the rest of this chapter, which I guess means for the rest of the class, because, this is the last class of the semester, we got to talk a little bit about math again. We got to work back to some of the math bits to this, which is actually ties right into these chemical reactions. And I'm going to talk about a man named Avogadro. If you look at a periodic table, the atomic mass of carbon is 12.01 AMU. A man named Avogadro worked out how many atoms of carbon did you need to have 12.01 grams of carbon. Now, traditionally, we always work out mass in kilograms. For chemistry, we work in grams. And so I say, okay, if one carbon atom weighs 12.01 AMU, how many atoms is 12.01 grams? And he worked out, Avogadro, who I'll talk about him more, that there's this many. That if you have 602.000000000000000000000 atoms of carbon, it weighs 12.01 grams. And as I said, this was worked out by a man most commonly called Avogadro. His actual name is Lorenzo Romano Amadeus Carlo Avogadro de Calenca e de Salato. And he said, if you have that many atoms of carbon, and this number is called Avogadro's number, 6.02 times 10 to the 23rd, that if you have 6.02 times 10 to the 23rd atoms of carbon, its mass is the same in grams as it was in AMU, just with new units. And he worked that this works for all things. That one oxygen atom weighs 16 AMU, according to the periodic table. That means 6.02 times 10 to the 23rd oxygen atoms weigh 16 grams. One gold atom weighs 197 AMU. That means 6.02 times 10 to the 23rd gold atoms weighs about 197 grams. Now, this is a huge number. If you had 6.02 times 10 to the 23rd softballs, it would be as big as the Earth. If you had 6.02 times 10 to the 23rd hydrogen atoms, and instead of them in a mass, you put them line by line, it could circle the Earth 1,000,000 times. If you had 6.02 times 10 to the 23rd Olympic shot put balls, it would be the same mass as Earth. But atoms are small. And so if you have 6.02 times 10 to the 23rds of a thing, it's a pretty reasonable size. What I have here is 6.02 times 10 to the 23rd atoms of zinc, aluminum, iron, and copper. Although this iron is really rusty, so some iron oxide. And if I pick this up and go to the other camera, you can see it's just like a small thing I can hold. It's like shorter than my finger. This is 6.02 times 10 to the 23rd atoms of aluminum. Now you note the volume isn't the same. That's because the densities are not the same, or the masses aren't the same either, but the size of an atom aren't the same for them. We talked about rates of atom changing. But all of these have exactly 6.02 times 10 to the 23rd atoms. And we know that mostly because we can get its mass. If we know its mass, we know how much 6.02 times 10 to the 23rd atoms of each of these weighs. That for aluminum, 6.02 times 10 to the 23rd atoms should weigh 26.98 U grams, because one aluminum atom weighs 26.982 AMU, so 6.02 times 10 to the 23rd atoms should be 62.982 grams. That's how I know that this must be that many atoms. Now you probably noticed that these have the words mole written on them, which I haven't used yet on purpose. You see, 6.02 times 10 to the 23rd is Avogadro's number, which is an amount of things. We define a mole as when you have 6.02 times 10 to the 23rds of a thing. And this can be confusing, but I always like to compare it to a dozen. You know a dozen means 12 things. If I tell you have 2 dozen eggs, that's 2 times 12, 24 eggs. It's a common idea that a dozen just means when you have 12 of something. It doesn't matter what. You can have a dozen eggs, you can have a dozen bagels, you can have a dozen, I don't know, pens. I think there's more than 12 on my desk. That a dozen just means 12 things. Well, a mole just means 6.02 times 10 to the 23rd. And you can have a mole of anything. A mole of atoms, a mole of eggs, a mole of bagels. Those examples I gave. A mole just means when you have 6.02 times 10 to the 23rd atoms. Since this is 6.02 times 10 to the 23rd atoms of aluminum, this is 1 mole of aluminum. And you can convert from moles to things in anything. That if you ever want to know how many things you have, if I tell you have 3 dozen things, you want to know how many things it is, you just say 3 times 12. If I tell you have 3 moles of things, you want to know how many things you have, it's just 6.02 times 10 to the 23rd times 3. Likewise, if I tell you we got 48, I don't know, 48 pens. There's a lot of pens on my desk. You could say, wait, 48. Yeah, 48 works. 48 is 4 dozen. 48 divided by 12, that's 4. Likewise, if I tell you a number of things, you can divide by Avogadro's number. You can divide by 6.02 times 10 to the 23rd to find out how many things you have. Now, in general, chemists work in moles. Chemists always work in moles. They don't like to say how many atoms something has. They'll never say, ooh, there's this many atoms. They'll say how many moles it has. And so if you go to a physicist, physicists don't use moles. They think they're dumb. And they would say something like, hey, we got a block of potassium. This block of potassium has 1.25 times 10 to the 21st atoms. A chemist will look at them and say, I don't fucking care. How many moles is that? If I ever give you an amount of things and you need moles, you just use these equations right here. And so if I tell you 1.25 times 10 to the 21st atoms of potassium and I ask how many moles, if you want to find moles, you just take the number of things divided by Avogadro's number. 1.25 times 10 to the 21st over 6.02 times 10 to the 23rd. And I'll just do that math. That math is 2.08 times 10 to the negative third moles. Any questions? I lost the bag for these in all my, there it is.
I faintly remember all this from high school chemistry, Dr. Lars. I took it in like 10th grade and like all the stuff. I remember talking about it, but not so much like the process of doing
Yep.
it.
Well, we'll go through the process. Fun fact, that's the last time I took chemistry also. So, you
Yeah.
know. Okay. Now here's the thing. Because of the way Avogadro's number was created, because of the way it means that the number on the periodic table, the atomic number, is the mass of one thing in AMU, but also the mass of a mole of things in grams. That means those numbers on the periodic table can be treated as the molar mass. See, instead of saying one atom of one atom of iron weighs 55.85 AMU, I can say 1 mole of iron weighs 55.85 grams. And what that means is every mole of iron weighs 55.85 grams. And I would define the molar mass of iron as 55.85 grams per mole. That if 1 mole weighs that much, that's how much each mole weighs. What this means is those numbers on the periodic table, what we earlier called atomic mass, is also molar mass. That molar mass is just how many grams per mole. And so we can pick up anything. Say oxygen weighs 16 AMU. That means oxygen's molar mass, 16 grams per mole. And if we know the molar mass, we can figure out how many moles you have of a thing. That I can go and take something and weigh it and say how much this weigh, and then say, hey, now I know how many moles it has. That's how I know this is a mole of aluminum. This is how we're going to interchange between having how much something weighs and how many moles of substance you have. Moles of substance being what is necessary to know when doing chemical reactions. Though we're not going to get that far, the point that why we need it, we're not going to get into this class, but the general idea is it goes with the balancing equations and this thing called stoichiometry, which is the bane of all chemistry students. Now, if I ask for the molar mass of any atom, any element, sorry, I misspoke, any element, use the periodic table. You want the molar mass of an element? Just read it off the periodic table. If I ask for the molar mass of a compound, you just find the total molar mass, kind of the same way we did with just atomic masses earlier. Let's say, for example, I ask for the molar mass of iron 3 oxide. Iron 3 oxide has the structure of Fe2O3. If I want the molar mass of iron 3 oxide, I'll say iron 3 oxide consists of 2 ions and 3 oxygens. And the molar mass of 2 ions and 3 oxygens is just the sum of 2 ions and 3 oxygens. According to this table, the molar mass of iron is 55.85 grams per mole. Also, according to this table, the molar mass of oxygen is 16 grams per mole. And so iron 3 oxide is 2 ions and 3 oxygens. So I would just say 2 times 55.85 plus 3 times 16. This means the molar mass of iron 3 oxide is 159.7 grams per mole. I kind of did this a little quick, but we've done this before. We did this before with atomic mass. It's the exact same thing, but in atomic mass, we said AMU. Now we're just saying grams per mole. We're just tacking a new unit on. Because moles were created in such a way that we can do that. Any questions? All right. Let's do an example. What's the molar mass of water? If I want to find the molar mass of water, water is H2O. It's made up of hydrogen. Hydrogen has an atomic mass of 1.01 AMU. The periodic table says that. That means hydrogen has a molar mass of 1.01 grams per mole. And the other bit of water is oxygen. Oxygen has an atomic mass of 16 AMU. That means it has a molar mass of 16 grams per mole. Therefore, the molar mass of water is twice the molar mass of hydrogen plus the molar mass of oxygen, or 2 times 1.01 plus 16. The molar mass of water is 18.02 grams per mole. Now, the reason we care about this, the reason it's important, is because molar mass is directly related to mass. You see, the molar mass is how many grams per mole. When I say the molar mass of water is 18.02 grams per mole, that means 18.02 grams is the weight or the mass of 1 mole of water. If I had 2 moles of water, it would be twice as much. And what we can say in general is that the mass of any compound will be the number of moles times the molar mass. Or I could rearrange, say the number of moles of any compound is the mass divided by the molar mass. These equations are often written as this triangle. The general idea for this triangle is if you ever want to solve for something, you've probably seen this in other forms, like it's used on a lot of things. But like if you want to solve for something, cover it up and it says the ratio. Then if I want to solve for the number of moles, I cover it up and it shows mass on top of molar mass. That means number of moles is mass divided by molar mass. If I want to solve for mass, I cover it up and I have number of moles next to molar mass. That means it's number of moles times molar mass. This triangle is the same thing as the equations above. It's just a way to remember it. But this will allow us to convert between mass and number of moles using just the molar mass, which is on the periodic table. Questions? Whew. Let's do an example. A standard bar of gold, which is a thing. A standard bar of gold is a thing that exists. A standard bar of gold has a mass of 14.474 kilograms. How many moles of gold is there? So, I'm going to say I have 14.474 kilograms of gold. Now, in chemistry, we need to work in grams. So, I know that 1 kilogram is 1,000 grams. And so I can do a unit conversion. I'm going to take my 14.474 and multiply by a ratio to cancel out kilograms and get grams. So I'm going to multiply that by 1,000. So if a standard bar of gold is 14.474 kilograms, that means it's 14,474 grams. Now, if I want to know how many moles of gold this is, the first step is look up the molar mass of gold. And so, okay, what's the molar mass of gold? Well, if I want the molar mass of gold, I'll take out my periodic table and say, there's gold right there. And underneath gold, it says 196.967. That means the atomic mass of gold is 196.97, I rounded to 97, AMU. And if the atomic mass of gold is 196.97 AMU, that means the molar mass of gold is 196.97 grams per mole. Now I asked for how many moles are there. As I said before, I have this equation. I had this equation. But I asked how many moles. So I'll go straight to that bottom one. Number of moles is mass over molar mass. I could also, if I so wanted, use the table and say number of moles is mass over molar mass. It's the same thing. And I'll say my number of moles is just the mass over the molar mass, canceling out my grams, doing this math. And I get that it's 73.48 moles. That is how many moles of gold are in 14.474 kilograms. Questions? Okay. That's it. That's the end. That is all the material for this class. You have made it to the end. Congratulations. Yeah, that's everything. You do not have a lab due this week. There is a homework due tonight, and there is also a homework due Sunday because I am an asshole. I will be doing a review session on Friday, and you have an exam on Monday. Yeah. This is my last lecture for you guys. It's probably one of my last lectures ever online since we're going to be in person next semester. Any last minute questions? Cool. It was interesting. I personally hate teaching online, I'll be honest. But it was interesting to do online. I will talk to you all later. Have a good day.